My name is Sebastian Avakian. I am a PhD student working with Tammy Barnea and William Witzak-Krempe, respectively, both at McGill, one at McGill and one at the University of Montreal. And so our research groups focus on looking at quantum matter and so naturally quantum entanglement. And so over the last couple of years, I'm sure many of you are aware of monitored circuits or hybrid circuits. It's become a very interesting system to study. And so today I'd like to present some work that we've done on these systems. And so this is based on our preprint that is available in the archive that will be updated soon of the same name. Okay. All right, so the outline for today is I first want to introduce what multipartite entanglement is, or genuine multipartite entanglement. And also, just to preface before, if there are any questions or something's unclear, just let me know. I know it's a little awkward through Zoom, but we'll try our best. After we talk about this multipartite entanglement, I will then discuss briefly quantum circuits and just what the measurement-induced phase transition is itself. And then I would like to explore this transition through GME, this multipartite entanglement, and how it kind of spreads and behaves in the vicinity of the critical point. And if time permits, I'd also like to talk about the scaling of our entanglement measures at criticality. Okay, so normally when studying entanglement, at least in my experience when I was first introduced to it during undergrad, it was a question of you have a state, you have a system, you trace out a part of the system, and you study the reduced density matrix on that system, on that subsystem, and you ask the question of, is it pure or mixed? And if it's mixed, then it's somehow we've lost some information from our in this tracing operation, and therefore we're somehow entangled, which is still true. But one way that we could think about entanglement is through separability. And so a separable state is, roughly speaking, one that can be factored into distinct parts. So for example, we could have some quantum state, and we could separate it into two, in which both halves are put into, or both parts are put into respective two different subsystems that, when comprised tensored together, make up the whole Hilbert space. And so we can then say a state is entangled if it cannot be written as a separable state. Now, this is fine for two parties, but if we want to generalize to m parties or just more, 2, 3, 4, so 3, 4, 5, 6, 7, then it becomes a little bit tricky because it naturally comes down to how we can partition our state. And so this is kind of the introduction to these multipartite measures. And so, just as I've already alluded to, typically we study entanglement through the density matrix. So for nomenclature purposes, this is what we call pure state. It's just the Brockett version, like so. And we can then mix our states together to get a classical mixture as we sum over some PI that form a probability distribution. Okay, so instead of doing the full general m-party case, we'll just start with three parties. So suppose we have some system that we can cut into three parties, A, B, and C. We can take some bipartition of the two. So for example, we'll just take A and we'll partition away from B and C, and we'll combine B and C together into another subsystem. Then we can write a physical state on the system, a pure state, that is, like so. So we just take the tensor product of the state on A with that on BC. Now, if we write it this way, we've naturally made it so that A and BC are non-entangled, because if you were to take any tracing operation, it would leave the other invariant. But it doesn't mean that this state rho is not entangled. It just means that there's no entanglement between A and BC. There can still be remaining entanglement in the subregion BC. And so if we take then the next mixture of all possible partitions I can have and weight them by appropriate coefficients Pi, Qi, and Ri, which also form a probability distribution, then I could form a general biseparable state. Now, again, in this negative version of our definition of entanglement, we'd say that the state is genuinely multipartite entangled if it is not biseparable. So if the state is not of this form here. Now, what this necessarily means is that I cannot have my parties, A, B, and C, such that if I cannot write my state this way, if it's not biseparable, that I cannot find a way to decompose my state where one party is removed from the other two. So in some sense, it's a collective form of entanglement that requires all of the parties to participate in some fashion. Now, determining if a state is entangled or not, in general, is a very hard problem, and especially if it's mixed. So determining if a state is of this form is a rather tricky task. So just before we proceed further, I'd like to just give a quick example of common GME states, which are more familiar than we would think. So a cat state or a normal like maximally entangled state is in the computational basis can be written as for 3 qubits or 3 spins as a combination of all up and all down. And there's also another kind of universality class that's not equivalent to the same kind of entanglement as this GG state, which is this W state, which is like a magnon or one of the spins being down and the other 2 being up. And so you can kind of understand.
Can you hear us?
Yeah, you can hear us.
Yes.
You misstated that state was maximally entangled. It is only maximally entangled for 2 qubits.
Oh, yes. Sorry, I do apologize. I will. Yes, that is fair. So these 2 are inequivalent in the sense that these, if you were to trace out one of these particles, so any 1, 2, or 3, you effectively have that the other 2 are unentangled. And one cute way to view it is through looking at these rings. So if you can somehow view carefully, you see carefully some kind of knot. If you were to remove one of these rings, the other 2 would remain intertwined and hence kind of entangled. Whereas in the W state, you would have that there is one spin that's down and the other 2 are up. And so if you trace one of them out though, and if you look at this knot, you would see that if you move one of the links, they remain, these 2 are unintertwined and these 2 remain intertwined. So there's an inequivalence in their kind of entanglement. And so if one were to try to create an entanglement criterion that were to detect a difference between them, it would need to be aware of these subtleties. And so there's no general way to study like a one-size-fits-all metric that just tells you, oh, it tells you all the breakdown of how a state is entangled. But we can create these criterion that can target specific kinds of entanglement. So if we look at the GHZ state, the cat state, one could create a family of criterion, which they have this W criterion, where effectively what you do is you take the RDM of 3 spins or a 3-spin the RDM of 3 spins, and you feed into this criterion, and it's a nonlinear function of the entries. And effectively, if this value returns to be positive, then your state is genuinely multipartite entangled for 3 qubits or 3 spins. If it's equal to 0 or negative, it is non-conclusive. So it could be entangled in some other way. This criterion isn't powerful enough to detect it. And we do this by maximizing overall local unitary operations. So we just rotate the basis and we try to find which basis it would maximize the entanglement in. Now we will use another one as well, which is another separability criterion, but it's a little bit more complex and it just contains the first one. But the take home is that if I have a positive hit, my state is entangled. If it is negative or 0, it is inconclusive. Okay, so changing gears. So I'm sure many of you are aware of what a quantum circuit is. It's just a form of, or one can think of it as a way to locally evolve a quantum state layer by layer. Usually it's comprised of, so is there a question?
No.
So sorry, the audio spiked. Apologies. It's comprised of unitary operators typically, but it can contain some non-unitary ones, as we will be seeing. And so effectively, it's just a product of operators. It's just, you apply this onto some quantum state, and maybe you use some diagrams where you can apply these unitaries in a way so as to make a final state. Now, the goal of the unitaries is to entangle, and we call them locally entangling unitaries. They could just be over a few sites, and our work will just focus with 2 sites, like a normal brickwork circuit. And the choice of unitaries that you use determine the final properties of the state. As is probably aware, I will use qubits, spins, sites, local degrees of freedom kind of interchangeably. So I apologize, but I can be more specific if required to. And also, I'm just also going to refer, if I do have a circuit, I will always try to emphasize in which direction time is flowing as well. So in our case, we will make the circuits, the unitaries random, which just means that we're going to sample according to some probability distribution, some unitaries from some set. And so we're going to be focusing on random Haar unitaries, which are, if you take the set of all unitaries acting on 2 spins, in our case, we'll just focus on 2 spins, we will sample these unitaries with respect to the Haar measure, which means just uniformly. But there are other things that are interesting. You could take different gate sets, like the Clifford gate set, You could even take a reduced gate set that's non-Clifford as well, whatever suited to your problem, or even just one gate in some cases. Now, as mentioned before, the operations don't. Yes.
Do you envision doing this? Are you thinking through this purely theoretically, or do you envision doing this on an actual device, or like what's the because like doing hard is hard.
Yes, yeah, exactly. Yeah, you're totally correct. Doing hard is hard. Doing this on, so we have some numeric work to discuss here, but we do not have hardware applications for the moment. It's rather difficult to implement the measurements. So precisely this slide, actually. And we've had some discussions with IBM about how this is doable or not, and it's a non-trivial challenge to do. So I guess I can answer that in more detail afterwards, if that's okay.
So you're gonna tell us about something that cannot be done?
No, sorry, I have numerics for these. So I haven't presented our results yet. This is just the setup, but I will be presenting some calculations that we've done with random HAR.
And that's like classically simulated, or?
Yes, yeah.
Okay. All right, continue on.
Yep. So, right, so we will have, so we will also allow some non-unitary operations. These will just be projective measurements. They can be in a specific basis. We will pick the Z one, but they could be more general. The idea is to just measure the spins along some axis in the whole chain. So we just pick one of them, measure its spin, and choose if it's going to be up or down based on the Born rule. And this is a way to partially kind of collapse your wave function. And it's to reduce the entanglement effectively in your many body state. And so these are non-unitary, which makes this a non-unitary circuit as well. So if we combine both of them, we have a competition between unitaries that entangle and measurements that disentangle. And if you, depending on how you want to mix these, you can actually get a competition between the two that can lead to a phase transition. And so here's the setup of the problem. So here we will have a brickwork quantum circuit. So now the spins are aligned with the horizontal axis. And on the vertical axis, we have time going upwards. And so the idea is we're going to apply unitaries in a brickwork fashion. And between each of the unitary layers, we will throw in projective measurements. Now, each projective measurement can occur on any site between the unitary layers with some probability P. And so here's a schematic from one of the first works on this. And the idea is just to have a state evolve under this. Now, if you consider the ensemble average, for some P, there exists a critical point. Sorry, for some, there exists a critical point such that for P below, we're in one phase, and P above, we're in another phase. And so this is said to have a measurement-induced phase transition, and it's driven by the measurements. And so a rough phase diagram that you can think of is if you take the entanglement entropy, for example, and look at different, and study the ensemble average of this quantity in different regimes, whether you're above or below PC. And so here, this is for entanglement entropy, but it can also be for other criteria as well. And so for P below PC, we're in the volume law phase. And so this is, you kind of think of it as there's not enough measurements, there's just lots of unitaries that are scrambling all the spins together, and you get this big soup state. Above PC, we get an area law phase, or really there's so many measurements that you're kind of close to a product state, at least in the very high regime. And then close to PC, you're in some moderate in between things. But there is a critical point, PC. And again, just to be clear, this appears in the ensemble average. So the circuit needs to be run, the final state needs to be kind of processed. Measurements are carried out for certain quantities, and then we throw the shot away and then have another one, and then ensemble average once we're done everything. So I would like to present a way to view this, which is somewhat related to the percolation picture for those of you who are knowledgeable with these circuits, and to basically study how we can think of GME or this multipartite entanglement near and around these phase transitions. So, okay, so here I have 3 different short circuits. Here now time is moving downwards, and we have 6 spins in each. Now I have Yes.
So I guess you have the entanglement transition in mind, right? Or the measurement, you have MIPT in mind, right?
Uh,
You're trying to
Right.
go near MIPT, correct?
yes.
Okay, and there are other measures and already like not try your multipartite, but maybe like bipartite measures. And
Mhm.
you're saying that we need a new measure because existing measures are insufficient for this particular transition? Or because existing measures are insufficient in principle? Your three-ring example shows how, multipartite can tell something when bipartite cannot. So I agree with that. But the question is whether there is something the existing measures of bipartite entanglement is insufficient for MIPT that you are going to address.
I see. So, firstly, okay. So one thing that's interesting. So I'm sure you mentioned before that random HAR is hard to study, and so here in our work we're gonna look at GME and random HAR, and in the bipartite case, actually determining PC is rather difficult. So even if you use the entanglement entropies or mutual information, the value that you can get is actually quite hard to pin down. And so many things aren't known about this transition, in particular the critical exponents, even for random HAR. And so here we're going to attempt to use GME and these entanglement criteria to hopefully get something close to understanding what these exponents should be like, if that answers your question.
But wouldn't this supposed exponent depend on what you look at?
Sorry, can you repeat the question, please?
Wouldn't your exponent that you're after, wouldn't that depend on what you look at, how you look at it, right? So, isn't that right?
So again, if I understand, yes. So obtaining exponents is a tricky problem. And in random HAR, it ends up bipartite, and in our case that I want to discuss today, is that multipartite as well is difficult to obtain, but it provides a view that hopefully we can use to get these scalings near criticality.
I think the question is kind of like, if you're thinking about an Ising transition, there's a different exponent for magnetization and for heat capacity and so on. So if you're defining a new property and this has some new exponents, then this is expected, right? Okay,
I understand. Yes. So
I'm trying to understand what do I get for the investment of learning a new measure. Essentially, I don't like to learn. So
that's fair.
I want to know what I get for my bang for the buck.
Yeah. So the take home message that I would like to get to is that you can actually get states that you can't get in equilibrium effectively, and these states appear near the criticality effectively. So in equilibrium, we cannot get, so for the grounds of the Ising model, we actually can't get these long range GME states. And here, we will see that in the random HAR close to criticality, we can actually, using these criteria, we can detect states that have this very long range GME that otherwise you could not get in, say, like an Ising model. So we'll discuss criteria that show this, and we'll explain how this can arise and why this is the case, and how you can hopefully try to engineer these states to appear that have this GME that doesn't just die right away, effectively. Is that more suitable?
I don't know. Maybe it is to be determined whether I want to learn this.
Sure.
It looks like I won't be able to figure that out until I try to learn it. It's a little unfair.
Okay, I will proceed if that's okay, and if it's still not answered by that point, then we can be glad to discuss.
In defense of the speaker, I don't think it's fair to assert you don't want to learn something until you've seen it.
I want to learn, I want to know what I'm going to get. I just like to know in advance how much.
So I just haven't gotten to the idea, but I'm
go ahead. Sorry. I'm just a very impatient person.
That's all right. Okay. So right. So if we have three different circuits here, this will be a way that we could try to visualize how one can carve out regions where we can have GME between different spins. So on the left-hand side here, I have, if you just look at the gray lines and the circuit, we can see that I only have 2 measurements at this point in this whole evolution. And on the other 2, I have more measurements. Now we'll focus on this low measurement regime. Now, if we could play a game where we apply a unitary to spins in our chain, and we can ask the question of, well, what unitaries are connected in which entanglement isn't impeded or measured and carved out? So here, these first 2 unitaries, they can be connected no problem to the following 2 here. But this one over here, it has a measurement that occurs that it effectively, well, it cannot communicate entanglement further in time to itself. So we can play this game and we can make these diagrams or these graphs, and we can try to see, well, what sites are kind of connected to each other. It's just basically like a light cone. Now, if I go to the many measurement regime, or the higher P regime, I see that I can't actually have graphs that span very far because I have too many measurements impeding the flow of information between the unitaries. And if you make the measurements just right, so if you remove some of these, you can actually get these graphs that connect many spins together. Now, why does this matter? So like we were discussing earlier, in the equilibrium case, in the transverse realizing model in 1, 2, and 3D, there's only GME, so this criteria that we're going to discuss, W, it only has entanglement if things are nearest neighbors. The second that you increase the spacing, it just drops to 0. And this is related to the death of entanglement. And under general conditions as well, we could also have that if you do a quench, or if you separate sites, or if you increase the temperature, you can actually have multipartite just disappear entirely. And lastly, it's also related to the monogamy of entanglement, which is that if I have 2 spins or 2 parties that are maximally entangled with another, roughly speaking, I cannot have them be strongly entangled with a third.
They can't be entangled at all with any other.
Yes. All right, so how are we going to proceed and actually study the entanglement in these circuits? So this is the protocol that we're going to follow. So we're going to create our Haar circuits, and we're going to fix a value of P for the circuit, and we're going to choose 18 and 24 qubits. We're going to then evolve the circuit that we have, and we're going to obtain the reducency matrix for 3 spins for a specific configuration that I'll just show in a second. And we're going to measure W, this criteria, for all of these separations that we can. And we'll have to do this process for many realizations, order of 10 to the 5, 10 to the 6. And finally, we'll ensemble average over all these values to get the separation. We'll get W versus separation for a given P. So, okay. So our results are that we get that our GME is long range. So let's break down the figures. So on the left and right, we have the same information, but presented respectively for 18 sites and 24 sites. On the y-axis and log scale, we have the ensemble average W value. And on the x-axis, we have the bond distance in linear scale, where the bond distance is defined as if I have a site I connect sites I plus X, and I plus 2X. So they make a triplet. And what we did is we chose 4 values of P. So for random Haar circuits, the transition is around at 0.17. So we picked 0.1, 0.17, 0.3, and 0.7. So above, below, just above, and far away from the transition in all the different phases. And so one thing that strikes first is that at criticality, we actually don't have the maximal amount of GME. So we actually have that just above the transition, we have that it is longer ranged. At criticality, we have that it still is long range and hits the maximal separation. So for 18 spins, there's only a maximum value of X is equal to 8. And so we do achieve this. Whereas for the 0.7 and 0.1, so when we're deep into the product, the disentangled phase and in the volume law phase, we have that it doesn't get that quite far. And I will return to in a second about how we can understand these far away from the transition, how we can understand them. And just to quickly go over for 24, we have much less realization. So for 18, we have a large ensemble of measurements that we can go over. Whereas for 24, we have much less. We have order 10,000 per value of P, whereas here we have order 100,000 in a million. So in order to understand why these results are the case, we're going to construct a more robust graphical representation rather than those little circuits with those little triangles everywhere. So if we take a subregion A and we consider the M parties in A, we will construct a graph that respects time that connects all M parties in the subregions. And we call this the minimal spanning graph, or Gmin. If no graph can be found, then we cannot have M party GME in A. So as an example to walk through, so I just changed my representation here a little bit. So rather than just drawing all the circuits and all the sites and the lines, it gets quite visually overwhelming. So instead, we're going to have time go to the right, and this will represent the whole evolution of our quantum state. And at each vertical bar is unitary. And so we have a repeating pattern of even odd Haar unitaries. And all of the horizontal lines are, if they are present, represent no measurement. And when there is no line, there is a measurement. And so we see that it kind of breaks we can see our circuit kind of in a way in which we can track which sections are connected and where clusters have been carved out. And so we can focus on this region here. So if we choose spins arbitrarily, 4, 7, and 10, we can try to construct a minimal spanning graph at this given time slice. So what we do is we try to trace, we go back in time and we try to find if we can find a couple of unitaries that connect them together. Now, this is in the moderate P regime. So this is when P is equal to 0.3. And the whole goal of this is to decide, okay, well, can I actually determine visually if I have some GME in my subregion? And so one thing that's not accounted for or not shown here is that just because I have a connection between my spins doesn't mean that they necessarily are entangled genuinely. Rather, they could have just 2-party entanglement and not 3-party entanglement in my subregion. And so one way to understand how we can understand this is through monogamy. And like was pointed out earlier, if the spins are strongly entangled in a subregion, then they cannot be strongly entangled with, or at all in some cases, just outside with people that aren't in my subregion or in the environment. And so here we have the minimal spanning graph in purple for sites 4, 7, and 10 at some time in the evolution. An example of what we call a parasitic graph, or a graph that connects our subregion to the environment that siphons away some entanglement, is shown in this dotted line in yellow. And so here, for example, for 4, 7, and 10, there is a parasitic graph that affects sites 11 and 9. And this is to help us understand that basically, at least in random Haar circuits, the values that W can have is rather continuous. And so this reduces the averaging effectively, because we have no hits for entanglement in certain cases due to these parasitic effects. Now, how can we understand the other regimes? Well, for the other regimes for low P, there's barely any, this really looks just like a brickwork wall, and that we actually have very little pockets of where regions are carved out. And one would expect, okay, well then we can most likely, given for a subregion, we should be able to find a minimal spanning graph that connects our 3 spins. However, there are very many parasitic graphs to this minimal spanning one. And therefore, they siphon away entanglement. Another way to think about it that's a bit more intuitive, I find, is that it's just a question of scrambling. So here we have so many connections between all to all, it's very difficult for the spins in our subregion to be genuinely entangled amongst each other if they are connected to all of the other ones effectively. And in the high P regime, we actually have a hard time finding a graph at all. And so one question we can ask is, in the figures that I showed before, it actually showed that actually for the area law distribution that we found that it actually was a little bit more longer range and slightly larger. And we'll get to that right here as to why that's the case. So what I showed you was a graphical representation of what the circuit breaks down in terms of where measurements occur and what unitaries are hitting it. But we could instead study more sophisticated measures that aren't just by eye during the evolution of the circuit. So on this axis here, what we're going to do is we're going to take those same 3 figures that I showed you, those graphs, and we're going to do the layer by layer evolution and calculate an entanglement quantity as a function of time. And so this quantity D is the distance from our state to the set of separable states. So effectively, you do this by parameterizing the separable continent and then taking a state and then optimizing over this distance. And the idea is that this captures all forms of entanglement, but it doesn't tell you if it's what kind of entanglement you have, just that it is entangled. And so it could be biseparable, it could be triseparable. So if you have a biseparable state, it would still give you a hit. So, okay. So for the values of 0.1, 0.3, and 0.7, we do this layer by layer evolution. And we can schematically draw what happens with this inset here. So this inset here represents the separable set of states, and the entangled set of states, or the C outside. The idea is that during the evolution of our circuit, if we suppose take the low P regime, what happens is that as the unitary layers keep hitting unimpededly our state, they slowly become more and more scrambled, and they start to journey into the set of separable states. Sometimes with some measurements, they can pop out, and then maybe they can be slightly entangled, but then throughout the evolution of the circuit, they keep falling back in deeper into the set of separable states. And so one way to kind of avoid this would be to measure it. But in the low P regime, there's not enough measurements to keep the state pushed out. As another extreme, one could imagine in the high P regime, where we have basically always a product state, but it's known that product states live on close to the boundary of this set of separable states, which means it doesn't take much for them to become entangled, only a few unitary layers, and you can get a small kick out of it. And in this moderate P regime, close to the transition, we can actually have where it's possible for very large spikes to occur. And so here, this is just a more quantitative way of describing that, where those three circuits described below, when there's a black star, it indicates basically that there is GME. And so we see that for the close to the transition, we have many spikes that occur where our state gets entangled. Whereas for green, we can have these moderate, like a strong hit, but there's not that many. And same goes for blue, where they can be weakly entangled, even though there are many unitary layers in the low P regime, and we have some entanglement, but it's never quite large. Okay. We can then turn our attention to the critical point. So if we go near PC, so in order to do this, we need to go to periodic boundary conditions. So those were for open boundary conditions before. If we go to periodic boundary conditions, we can get a little bit a nicer sense of how large our system should be and reduce the effect of open boundary conditions. So one thing that I didn't mention was that in our minimal spanning graphs, what happens that if we have a notion of parasitic graphs, or how sites can siphon away entanglement, sites at the edges of the chain have an advantage and have entanglement promoted, because there are less sites to the extremities of those edge sites that can take away entanglement. If you make the boundary conditions periodic, then these edge sites are no longer safe from that and can have more parasitic graphs that can effectively remove their entanglement or reduce their entanglement within the subregion. And so here what we did is we performed the same kind of analysis, but now on log-log scale for n equals 24. We have around 100,000 samples and order 10,000 samples for other values of P. And we just effectively just crossed the transition. So we started just below to just above. And we wanted to see effectively how W scales as we get near the transition. And so the first thing to note is that it actually increases monotonically as you cross the transition. So there's no discontinuity. And importantly, for n equals 24, there's up to x equals 8 for our separation. But we never really achieved this because the periodic boundary conditions make it such that, again, like I said, it's much harder to get an entangled hit. And so there is no GME at maximum separation, yet it's still long range, just not as long range as the open boundary conditions. And we can try to use this to get a scaling with separation effectively. So we can narrow down to the critical point. So now I will have to reintroduce our other criterion I2, which is a more powerful criterion of entanglement than W. It includes it. And it's more robust as well to for larger hits where entanglement's harder to detect. It picks up features it picks up those hard to find hits. And the optimization required for it is a little bit more intense. And on the left as well, we also have something called the logarithmic negativity, which is a two-party criterion. So in this case, it's just for 2 spins. And so it is not for 3, but it's an exact quantity in that it's exactly computable, not like the other 2, which we need optimization over. So because there's no optimization, it gets a little bit cleaner for the scaling. So again, here on the left, this is just a 2-party value, and we're just going to fit these at criticality in log-log to some power law. And we find at criticality for in random har that we see that the negativity has an exponent of around -7. And for W and I2, they have very similar exponents. and they're around 8.8, 8.7, 8.9. Now, to be very clear, it is very difficult to estimate these because one of the fit to, at least for the three-party case, like the optimization becomes incredibly difficult at larger separations. So the uncertainty on these are of much higher, but present a first order attempt at these as well. Very importantly, though, their finite size effects are rather intense in these systems as well. Just as I mentioned, that it gets quite hard to get many separations, and if one is to extract a power law scaling, we really need the tail of these functions, and we don't quite have these tails, at least in smaller circuits. Okay, so of this work, there are many remaining questions. Effectively, kind of what scaling with separation can we see for a stronger GME criterion? So W and I2 are sufficient, but they don't capture all forms of GME that are useful, or that are interesting rather. We can also ask, are there ways to stay in the random Haar picture but make these exponents more precise? Like, is there a better methodology to doing this? I think one of the most straightforward things to ask is, what if we just make the regions larger than one spin in each of them, or one qubit each? And so, for example, taking arbitrary size regions of different parities, so it can be even, odd, even, or 2, 1, 2, or 2, 2, 2, or 2, 2, 1, for example, and studying how those scale. They're different. And do we also have this kind of long-range behavior where you could generate these GME states that are really separated in higher dimensions, so in 2D, so specifically in Clifford cases, for example, if this would be possible to do. In 2D, I do not recommend doing random Haar in 2D. It's very difficult. But yeah, and I just want to thank, first off, my supervisor, both of them, so Tammy and Will, and Luque, who did the work on the icing models, was also very useful in learning about these. So I'll leave it at this slide, and just want to thank you for your attention.
All right, thank you. Questions? I have one. So can these new measures that you see in the exponents and so on help us zero in on the value of PC?
So that was one of the goals of this work, I will admit. It turns out that one would need a criterion that doesn't have, the difficulty of optimization. So the optimization at large separation is quite difficult, and one that can actually detect, robustly detect at large separations, not like just on its own. W is not that strong of a criterion, but the goal is effectively to get close to them. There have been studies though using the mutual information that are rather robust. But random Haar specifically, these Haar circuits are difficult to get a sense of. So one would probably have to use a different gate circuit, a different set of gates to probably answer that question.
Other questions? All right, so let's thank the speaker one more time.